Hello, this is Dr. Christy Patton-Lokes, a chemical engineering professor at Missouri S&T. In this video lesson, we will begin discussing numerical differentiation. So let's first remind ourselves from our early days in calculus when we first learned about the definition of the derivative. And the derivative is the limit as delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. So it's the slope between 2 points on a curve as those 2 points get closer to closer, and that's what we call the tangent to the curve. To estimate the derivative, we can use this definition, and there are many ways you can use it. You can use a central difference, which is basically what's shown in the picture, that if you take a point and go a delta x to the left, a delta x to the right, estimate at those 2 points, and then that is your two values of f of x, and then divide by the distance between those two x values. That gets you a central difference. But we can also use a forward difference or a backwards difference. A forward difference looking at the point x and the point x plus delta x. A backward difference looks at the point x and the point x minus delta x. So the difference forward or backward is based on the location of x. If you want to evaluate the error estimate, then the way we can estimate that is using a Taylor series estimate. If you write out the Taylor series for a function, f of x plus delta x is equal to f of x plus delta x times the first derivative of x plus delta x squared over 2 factorial times the second derivative of x plus the delta x to the third power over 3 factorial, third derivative of x, etc. So if we're looking for f prime of x, I can solve for f prime of x as f of x plus delta x minus f of x over delta x, plus some other terms. And these other terms are this grouping here divided by delta x. Now if delta x is small, multiplying by delta x, remember delta x squared over delta x will be just delta x, or delta x squared, because delta x cubed over delta x is delta x squared. When delta x is small, this will be much smaller than this. So as long as I'm keeping delta x to be small, then the remainder is going to be on the order of the size of delta x, because everything else will be enough smaller that I don't need to worry about that. We can also do a second derivative estimate. And again, we use the Taylor series as our motivation for this. If you take the same expression for the Taylor series, then you get an f double prime of x in there, right? Okay, but I want to eliminate the derivative terms. I'm assuming I don't know what that derivative is, right? If I knew what the derivative was, I wouldn't need to numerically estimate it. So one way to eliminate that piece is to look at, instead of just going x plus delta x, let me also do a Taylor series for f of x plus 2 delta x. Okay? So if I do that, then I'm going to have these terms that are just functions of, x plus delta x and x plus 2 delta x, and functions of x, and then I have these pieces that have the derivative. The derivative is the problematic part. So I'm going to subtract these in a way that those terms are eliminated. So we're going to multiply a by 2 and subtract b. And then when I solve for f double prime of x, I end up with this expression. So f of x plus 2 delta x minus twice f of x plus delta x plus f of x over delta x squared minus, and then I have my higher order terms. But again, this time I'm dividing through by delta x squared, so it's going to be delta x times, and there's an 8 over 3 factorial divided by 4 over 2 factorial. Okay, so that's left out of this. But it's going to be delta x times some other stuff, and everything else will be even higher order, which means even smaller. So this is the second derivative. And if you look at this, this kind of looks a little bit like maybe a squaring, right? If you took x minus y quantity squared, you'd get x squared minus 2xy plus y squared. And recognizing that pattern, and if we were to go ahead and do this for third derivatives and higher order, and those are done in the notes, then we can get this other notation that's going to be very handy. So one thing you can do is, let's just call it f sub I instead of the parenthesis, and f of I plus 1 means I've added a delta x to my x. Okay, so I represents at x, and I plus 1 means I've added delta x. And so delta f of I means that I'm looking at the change in the function of with delta x, okay, at point I, or x. And so delta f is f of I plus 1 minus f of I. And so based on this, we end up with this forward difference notation that this delta f, and I can't type that upside down delta very easily, so I have just left it as a normal delta, but this is another way of writing it frequently. But anyway, the change in this f sub I over delta x plus some terms that are on the order of delta x small. That's going to be an estimate for my first derivative. And for my second derivative, it's f of I plus 2 minus 2f sub I plus 1 plus f sub I over delta x squared plus some terms that are of order delta x or smaller. And we can then use the shortcut notation. The delta of delta fi is going to be delta of fi minus delta of fi minus 1, right? Because that's what the delta means. And so I can evaluate the delta f sub I. It's f sub I minus f sub I minus 1. But then it's the delta of that. And now then I can apply the definition for delta to this. I can apply the delta definition to this. We end up with these terms. These two are the same, so I end up with this. This gives us a really streamlined notation, which says that f double prime of x is delta squared of fi over delta x squared plus those error terms. And if I go to even higher order, I can continue this pattern by noting that delta to the nth power is always delta times the one smaller than it. And so therefore the estimate for the derivative is either of these two notations here. And the difference between the delta, the normal triangle, and the upside down one is whether I'm using a forward or a backward difference. Okay, am I counting from x adding delta x or subtracting delta x? And it really shouldn't matter which one you're doing as long as you are consistent in the way you're doing it. But in all of these, we're going to have answer that is on the order of delta x close to our answer. So however close I need to be, I need to choose a delta x that is appropriate to get my error limit. So this concludes this lesson. In the next lesson, we're going to come back and look at how we might get just a little bit closer. Thank you very much for your time.